eventually we'll want to make a measurement, and we'll hope that our measurement picks out the state A. But at this point, the amplitude of A in our state is just the same as the amplitude of anything else. Its phase is different, so but its amplitude is the same. We need to perform some other operation that will turn this phase information into amplitude information and enhance the number state A relative to other states. It turns out that a useful and, in the end, under certain assumptions, optimal way to do that is to use what's called the diffusion operation. Or to exploit an operator D, which is diffusion. And D is the following operator. It's reflection around our reference state S. Remember, S was just the sum of all the number states with equal amplitude. So this on S is 1, on any state orthogonal to S is -1. So it's another kind of phase thing, but it's reflection around the state S in Hilbert space, as opposed to reflection here of just A0. Okay, well, it's easy to write down this thing. What is it? But the rule of the game is we're supposed to write down things that can be realized using a sensible arrangement of a finite number of gates. Here's how you can how you can realize D in a way that one can imagine would be practical if one had access to qubits and quantum gates. Namely, D is the tensor product of Hadamard gates, the thing we saw before in turning the state 0 into our reference state. So it's a product of three things. This tensor product of Hadamard gates, which turns, as we saw, the state 0 into the reference state S. It also changes, on the contrary, it also changes S into 0, back into 0, because it's easy to show that h squared is equal to 1. I should have mentioned that, actually. But it's extraordinarily simple calculation to show that h is its own inverse. Okay. So by acting with our reference state, acting with this on our reference state, S, we turn it into 0. Then we reflect around 0. Then we turn 0 back into S. The combination of doing all those things, this is like a change of basis from interchanging 0 and S and reflecting around 0 is to make a reflection around S. And this thing is something that you can implement. So this is 0 is a fixed number state, remember. Using n or maybe little n or maybe little n plus 1 gates. Because what you have to do is on your qubits, remember you have n of them, have a gate which distinguishes whether that qubit is in the 0 state or the 1 state. And then if and only if all of them are in the 0 state, change the sign. And then, to get precisely this form, change the sign of everything. So that, which can be done with simple 1-bit gates that change sign, change the sign of the thing they act on, change the phase by a factor of -1. Okay. So. I won't, unless really someone insists, spell this out anymore. It's a very good exercise to try to draw a little circuit diagram that shows how you implement a phase change just on one particular state without touching that one particular fixed state without touching the others. You can draw a little wiring diagram to show how to, and simple gates that implement that operation. So D is something that you can realize with a small number of very simple gates, namely gates that implement this and are Hadamard gates that we were using before. Okay, so we have two building blocks, the operator D, which is a unitary operator, and the operator U, which is a unitary operator. In fact, we can keep that last bit implicit. It's always going to just be sitting in this. The register is always going to be sitting in this state throughout the whole operation of the algorithm. And now, from these two ingredients, so this one, again, is the oracle. It shifts the phase of A relative to everything else. And this one shifts the phase of S relative to everything else. Shifts the phase of A0 relative to everything else. This one shifts the phase of S relative to everything else. The first operation gives us a phase depending on A0. The second one then turns that into an amplitude modification of A0 relative to all the elements that aren't A0. So the precise form of that remark, that's also quantitative, is we define G, the Grover operator, equal to D times U. And we can calculate how it acts within the two-dimensional subspace of Hilbert space spanned by S, our reference state, the one that had just all the number states equally represented, and the special state A0. Okay. Neither U nor D will take us out of this two-dimensional space once we're in it. This one, it's reflection around S or reflection around A0, basically. So those are the only two directions in town. And so we have to just see what happens within this two-dimensional space to see how G acts. If we start our calculation in the reference state S, we'll never get out of this two-dimensional space. So it's a straightforward calculation then to calculate the matrix that represents G within that two-dimensional space. Let's use a convenient basis, which is A0 and the vector perpendicular to A0 in that space. Which is simply 1 over square root of n minus 1 times the sum over all a not equal to A0. Or, of course, you can write it as getting the normalizations right. Square root of n. This is equation 12 in the notes, slightly rewritten. A0 perp in terms of S and A0 is we just take out A0 and renormalize. Okay. So it's a straightforward and not terribly involved calculation, just following the definitions to figure out the matrix representation of G in this two-dimensional space. I'll just write the answer here. It's G equals 1 over n, and then n minus 2, 2 square root of n minus 1, 2 square root of n minus 1, with a minus sign, and n minus 2. It should be a unitary operation. In fact, it's simply a rotation in this two-dimensional space. For n large, it's not very different from the identity transformation, just a little bit. That's because, that's easy to understand, U, remember, just imparted a slightly different phase to A0. A0 is a small part of the whole vector S. So making that phase transformation on a small part and then reflecting doesn't do very much. But it does a little bit. It does a 1 over square root of n kind of operation because acting on a piece of the vector that has amplitude 1 over square root of n. So that's G. And now we're almost done. Let's just write G as a rotation, which it is. So sine theta is exactly 2 square root of n minus 1 over n. And for large n, theta is a small angle, 2 over square root of n. Therefore, as a special bonus, you find that the representation of our original vector s over here is let's see, I forgot if I'm putting A0 on top or on the bottom here. Yeah. A0 is on the top in this two-component representation, and A0 perp on the bottom. So our original S is like that. It's almost all A0 perp, but the same angle appears. And so, if we apply G, the Grover operator, L times, to our original reference state, S, which is this, the result is G to the L S equals sine L plus 1/2 theta cosine L plus 1/2 theta. Okay. Just rotate L times theta.
So this representation for the state of S, what's the base?
The basis? The basis, this is A0, and this is A0 perp. So we write it in orthonormal basis so that rotations take a nice, we have rotations in a nice form. And you see, if we choose L properly, we can make this component be almost 1. So we can get, by repeatedly operating with U and D, doing this kind of phase transformation, reflection, which can also be thought of two kinds of reflections. We can single out the A0 state very, very accurately. So with L plus 1/2 we want L plus 1/2 theta to be pi over 2 in order to maximize the sine, approximately. Remember, theta is very small, so that we can get a pretty close spacing of the possible values, even though L is an integer. So with this, the proper choice of L, namely L equals about pi over 2 theta minus 1/2, and theta given over here we can get our vector, our original reference vector, massaged so that it becomes almost all in the A0 direction.
Instead of L has to, I mean, does the L have to be of the order of square root?
So L is of order square root of n, exactly, right? Because it's the inverse of this theta is the dominant factor. It's basically pi over 4 times square root of n. Up to 1 over n corrections. Okay, once we have, so now inside the quantum computer somehow is the answer. We've concentrated a wave vector on, concentrated the wave function on the number state A0. Now we make a measurement. You read out the value of each qubit so it's n separate measurements, if you like, little n separate measurements. And with high accuracy, because we've produced the number state A0, these measurements will read out the binary expression of A0. Okay. So that's the Grover algorithm. You take square root of n steps, square root of n consultations with the oracle to read it, to learn what the hidden value A0 is. Yeah.
So technical question. So each time you consult the oracle, you do little n operations by
No, you do one operation. Well. Oh, well, yeah, you're doing n, but they're all in parallel. You can do, they're all acting separately. So it's 1 unit of time. Okay, it's little n units of space, if you like, but 1 unit of time, almost. Yeah. So there's a lot of parallelism going on in the intermediate steps. That's the yoga of this. That there's a lot of parallelism going on in the intermediate steps, orchestrated in such a way as to enable you to look through the list in square root of big N steps instead of n steps. We have a few times little n gates. We have these Hadamard gates, one for each qubit, and we also have a system of gates which enables us to single out the absolute zero number state among all the rest. So that also takes about n gates, little n gates. Controlled NOT gates that tell you you want to concentrate when every single qubit is in the zero, and do ands so that you can concentrate on just the one state where all of them are zero. Okay, are there any questions about that? Okay, that's all I wanted to do today, and tomorrow we'll show that it's optimal, and show some of the things you can use it for, and then we'll question the optimality. So the optimality proof will, of course, have some assumptions. We'll cast some doubt, perhaps, on those assumptions. And, yeah.
So this really shows explicitly the number, how many times you can find the target. It's like this really
Yeah, this is very, very concrete. There's no, there's nothing hidden here. It's absolutely,
like a search operation.
it's a very specific, it really is an algorithm. It tells you exactly what you have to do. Right? And if you had a quantum computer and wired together the gates properly, you could program, well, actually the wiring diagram is pretty much the program. You just crank through.
I was thinking something related. What if you cannot separate a state you are interested in from the rest? Usually call the rest A0 proof, right?
Yes.
Suppose there's always interaction. Those states
Oh.
are not eigenstates. Somehow there's always a
You absolutely do not want your quantum computer to be interacting with the external world. So there's a very elaborate story of error correction if you do let it interact with the external world. And well, it's a very elaborate story. I'm not going to go, but it can be done in principle. It requires using more gates so you can check things, and it gets quite a bit more complicated. But in principle, it is possible to allow your quantum computer to interact a little bit with the external world and correct for it. Just as and if you have a classical computer, if the external world could foul things up, and that's why you do parity checks and things. And so there's a quantum analog of that kind of procedure. But it's much more subtle because sort of the name of the game is you're not allowed to make measurements until the very end. So you have to correct errors somehow without measuring anything. And that's quite tricky. But it's proved with certain assumptions that we'll discuss that you have to use of order square root of n calls to the oracle to solve this problem reliably. Yeah. There's no way to do it faster with fewer calls to the oracle. I'll prove that tomorrow. Right. And the basic thing is that the oracle doesn't do very much. It only acts on one. It only distinguishes one state from all the rest. So mostly it does nothing. And if it's what?
L has to be over.
L has to be root n, right? So that's the root n that tells you how fast the algorithm is. It takes root n calls to the oracle. Yeah.
I have a very silly question. I think according to the method of the quantum calculation, you can act on every qubit simultaneously. I mean, you can act in a parallel method. But
Yes.
In the classical calculation, you have to act on one particle or one bit, one at a time.
Well, it's not so different, really. The quantum computer acts with some number of gates at each time interval. You have a number of gates acting. Typically, the number of gates is of order the number of of qubits. Not all of them might be active, but that's how many you have. And and you step through. Classical computers the same way. You have a whole bunch of gates that act on registers, and they act on the whole. Each gate is acting on a piece of the register, but you can think of the whole thing as cranking through a global operation on the whole register. So each gate has to act locally, but they act all together. The difference between the quantum computer and the classical computer is that the quantum computer can have superpositions. So you can be acting on many, many different states at once. But for each particular state, it's very much like a classical computer. Does that answer your question, or I'm not sure what the question was?
The question is, it might be unfair to compare the time, it would be unfair to just compare the number of the steps of the quantum computer and the classical computer.
Well, it certainly is unfair with present-day technology, yes. Quantum computers are much slower, and it's much more difficult to construct gates and so forth, but just for purposes of having a standard of comparison to normalize things, and you can change the normalization if you want, and that'll tell you how bad things are. But for an equal number of gates and an equal number of steps, the quantum computer in this particular application is doing better because it's changing n into square root of n. Yeah. So if n is large enough, even if, say, the quantum computer gates are 1,000 times slower, if your problem is 1,000 squared size list, the quantum computer is doing better. So for large enough lists, eventually, if quantum computers can support many, many qubits, and if the gates get reasonably fast, there is the possibility of gaining something. That's not going to be, at least for this pure list search, it's going to be a long, long, long time before quantum computers beat the best classical computers, if ever. But in principle, they can. And in other applications, the advantage may be greater. Yeah. Mhm. No, the oracle doesn't do the measurement. You do the measurement by the way you do measurements on your two-state system. You see which of the two states it's in for each of the separate bits. That's a measurement. You do that at the end, right? Until that time, you have only unitary evolution. It's at the very end you make a measurement. Right? The oracle does not make a measurement. The oracle implements a unitary transformation. That's really crucial. Yeah. Okay, thank you.